Good morning.
Yeah, good morning, sir.
Yeah, very good morning. Yeah. So, so the next week will be your test week, right? So there won't be any classes in the next week. So again, so anyway, however, we have a test on Tuesday, so we'll meet on the test. And the next week, the next class will be after that, the next to next week, right? The Monday, that is on 28th February, and you will see that. Uh, so any questions? So I have sent the details. Anyway, we discussed that in the last week, last class about the exam and all. So even I have sent an email. So please, all of you join the teams just 5 to 10 minutes before that. Anyway, I created the Teams link also. So it will be there from 9:30 onwards. But the paper I will just upload just 5 minutes before that, around 9:55 or so. You can start take the exam on from 10 onwards. And during the exam and all of you should present through the teams and all. Right? Anyway, however, you have to write through the conventional, the pen and paper, but you should be make it available through through teams and all. And the exam is for 2 hours. And so we have within the 10 minutes after soon after the exam, within that you need to submit to the your respective TAs, and even that contact list of the TAs and your group wise details. So those things again I have circulated through email. So please look into that. And the same list is also available in the teams also. And in that actually for every group there are two TAs for that. So one TA for for assisting you for computer architecture, and other one is for OS. So you need to send your answer sheet, answer script or PDF format to the TA who is assisting the CA for your group. So those details, all the details are available. So please go through that prior to the exam itself properly, and then do be carefully and send the documents to the respective TA. Okay. So okay, anyway, then let me start today's lecture. Yeah. So is this slide visible? Computer
Yes, sir,
system
it's visible.
organization, right? Is it visible?
Yes, sir, it's visible.
Okay, great. Yeah, I think now it's visible in full screen mode. So in yesterday, in the last class, actually, we just started the introduction to OS, and as I have mentioned that the concepts that are whatever we are discussing the OS, since we already covered the architecture and all, so you can able to get a feel for that because basically the operating system used to manage the computing system, the basic hardware and all. So in that aspect, actually, whatever we discuss, whatever we learned so far, so that will be helpful. That will be useful for your understanding and clarity on what is the role of OS, how it manages, and also all those things will be useful in this context. So before going to the details of OS, as I mentioned that first of all, we should be aware of that what are the various components where the computing system consists of. So those aspects we have discussed in the last class. So at a very gross level, you can view the computing system something like this. It contains one or more CPUs and have a memory unit where the CPU can access directly that. And it's not, I just mentioned here as a simple memory and all. So it will be like hierarchy of memory will be there, like, and you have a disk, it's a hard disk, it's a secondary storage will be there, And then we have other peripherals like printer, keyboard, mouse, and a monitor, something like that. And you can see that there are varieties of devices that are connected to computing system as a part of the system, as a peripherals and all. So the nature of these systems are very different. Some of them here, if you look at the disk and all, this is for storage using a magnetic disk, set of disks and all, where it can be used for either you can able to read from the disk information and you can also write into that, right? And there are other things like you have a mouse which can be used to access the computer through graphical user interface, and have keyboard where you can able to enter the data by user and all. Or you can, for different applications we can use it, like for word processor and all those things we can input the data by using a keyboard. And printer, and likewise monitor you can display. And have a memory, main memory, where the CPU can access the data or instructions from this. So all these are connected by bus. And now how the system can make use of or can interact with all these devices and all. So that will be done by taken care by the operating system. And we have seen that there are various peripherals and all of them have their various characters, different characteristics. The nature of the devices will be different. So that some of them are the bidirectional, some of them are the unidirectional. Like for example, if you take the discs and all, so it's a bidirectional. That means you can able to read from that and you can also write into that, right? It means that the disk can take the input as well as it will give the output also. Whereas some of them will be like unidirectional. Like for example, keyboards, it just give by pressing using a keyboard, you can able to insert or you can able to input the characters, input the data, right? Whereas the printer and all, it's output device, like the data transmission or information transmission will be from a computer to a printer, whereas a keyboard will be in other direction. Likewise, the mouse also. We have a monitor. So likewise, all these devices or peripherals, they have their specific characteristics. So to deal with these various peripherals, each peripheral is associated with its controller. Now, suppose the disk, we have disk controller and we have ESP controller where multiple devices can be connected. We have a graphics adapter where your monitor will be connected. So likewise, for each device, it has a specific controller, and this controller will monitor or will be used to control the like either reading the data or writing the data. So all these aspects will be taken care by the disk controller. It's basically, it contains maybe set of registers and some buffer and some specific processor also will be there. So likewise, the disk controller used to manage the that particular specific device. So likewise. So now as a system, if you want to use the user, if you want to make use of or want to interact with these systems, the user cannot interact these things directly because each of them have different characteristics and you cannot do that. So therefore, the operating system used to manage or used to interact with these all these devices by using these controllers and all. So each controller used to manage the specific device. So therefore, for interacting with these devices, the operating system uses a specific piece of code for every device. Like for example, have disk controller. To interact with disk controller, operating system contains a specific piece of code known to be like a device driver. So that particular device driver will be used to interact with the disk controller. And likewise, there is some other specific device controller used to interact with the USB controller. And other device controller used to be device driver used to manage the like a graphics adapter. So likewise, the operating system used to maintain like varieties of device drivers where each device driver used to interact with a specific controller, specific device controller. So with that, the operating system used to manage to interact with these peripherals on behalf of the user and all. So user cannot interact all these things directly with these peripherals and all. So whatever the user wants, suppose user want the input from a keyboard, you can see that in a high level language, you write the scanf function. So using the scanf function, he tries to or he attempts to interact with the keyboard, like accepting the data from a keyboard, right? But internally, that scanf used to make use of like it's a function call and that function call will internally make use of the operating system, and with the help of operating system it used to accept the data from a keyboard. Likewise, if you want to write something, if you want to access the files, so likewise from the disk also the user tries to attempt to access the disk using appropriate function calls, and these function calls will in turn make use of the operating system routines to handle the specific data input or data output, whatever it is. And we'll see that how these things are happening, and these things we have discussed, what the device controller will be, what it contains, and all. And for example, as I mentioned here, for example, as a user program, it requires some input from a keyboard. Then what you are doing then, at a high level language, we'll just express that in the form of a library function like scanf, and when the CPU interacts with that scanf function, which tries to execute the scanf function, it realizes that it's a library routine, and when it tries to execute that library function call, that library function call will internally make use of the operating system and all. So it means that the operating system will initiate the IO, like input output operation, by the given for the given from the given peripheral and all. Then afterwards it will initiate IO, but these devices are very slow compared to the operation computer, compared to the speed of the CPU, because as you see that the CPU will operate at a rates of clock speeds like 2 gigahertz. That means 2 into 10 power 9 cycles per second. In each cycle, an instruction can be executed. Whereas here, these devices, these peripherals, they are very slow. Like as we see that when we want to input the data from a keyboard, we can see that our natural speed will be maximum, like at order of like 10 or 20 characters, or maybe 4 or 5 characters per second, or something like that. So there is a vast difference between that. So therefore, when we want to take the input the data from a keyboard, for example, we'll initiate that, and after that this IO controller, whatever this the particular device controller, it used to manage to collect the data from the particular peripheral, and once the data is available, then after that it will inform to the processor, because the processor will not wait cannot wait for such a long duration for a specific task, because if it requires IO input from a keyboard, then by using a function call, it requests the operating system, and the operating system will internally contact this particular device controller in the form of that it writes something into the device controller's register, and with that the device controller will come to know that the operating system or any user process is expecting something, and with that the device controller used to will be ready to accept the data from a keyboard, and then once the user press the key, with that the corresponding data whatever is arrived, so it will be stored in a local buffer, and once it is available, then it will inform to the CPU. So the way it informs to the CPU will be, because the CPU will not wait for that particular the user input. So it tries to it tries to run some other programs in the meantime. So whenever this IO completed, that will be informed to the CPU by generating the interrupt. It means that, because otherwise CPU doesn't know. CPU will execute the user programs most all the time. And whenever it requests IO, it will inform the IO, it will inform the operating system, and operating system will in turn will make use of the device driver and other things. It will inform to the device controller, and the device controller, whenever it receives the information, and then after that, then it will inform to the CPU saying that whatever the data you requested, that has been available now. And then it will send the interrupt. That means it will send a signal to the CPU saying that the data is ready. Then the CPU will again make use of operating system to transfer the data from the device controller to appropriate location to memory and all. So that way you can able to access the data, can use to manage the peripherals by using the operating system and all. And for doing that, we'll make use of interrupts. We know that we already know that interrupt is nothing but the unusual the event that is happening in the process of execution. Otherwise, the CPU will execute the user programs, right? User programs are kernel programs, right? Or system programs. And if when any unusual thing happened, then it will be informed to the CPU. Otherwise, the CPU executes the user program, and it is requested IO. But whenever the IO is completed, at that time, the device will send the signal. Then the CPU will see that what this interrupt, what this signal corresponds to. Then based on that, it realizes that yeah, this signal is corresponds to a particular IO device and all. Then it make use of the operating system to perform that particular task, to perform the again transferring that data from that particular USB controller to the memory unit for the particular specific memory location. So that will be carried out by using the interrupts and all, by using an interrupt. We'll see that what is the interrupt and all, how it happens. Yeah, now the various common functions of interrupts. Actually, here these things actually we have already had some knowledge about these interrupts, which we had discussed in the last I think 3-4 lectures back before and all. And here we know that the interrupt means something, some unusual event that something occurs, and that will be informed to the CPU by using different means. One thing is that by using suppose there is something happened like some power failure or some device has malfunctioned or something happened, or otherwise if you allowed some, if you gave some task to the a particular peripheral and that has been completed and that will be informed. So all these things are by using, it will send some signal to the CPU like externally, and at a particular pin of the CPU the signal arrives. Then the CPU will realize that yeah, there is some signal or there is some request from the peripherals or somewhere other than the processing unit and all. So then once the signal is arrived, then the CPU will check that. So what is the signal, like why, from where the signal is arrived, from either from the disk controller or from the keyboard controller or from the like some other peripheral and all. So for that purpose, it will make use of various things like either by using a polling technique. It means that once the signal is arrived, then the CPU should aware of that. CPU should realize that actually what is the reason for this particular signal, which device has caused this interrupt and all. So for that purpose, actually the CPU will make use of techniques known to be polling, one of the techniques, or sometimes it will use the methods known to be interrupt vector. So with that, actually, when you're sending the signal or when you're generating the interrupt at that time itself, you also will generate a corresponding number, a corresponding interrupt number. So with that, whenever the interrupt arrives, then the operating system will check that actually which device has been caused the interrupt, or like what is the reason for this interrupt and all. So that way, by using this interrupt vector or like polling techniques, we'll come to know about actually. So what has been caused this interrupt, right? And then accordingly, because for every interrupt, there will be specific routine used to be there. There will be specific service routine used to be there. And by using the service routine, that particular event has to be handled. Like for example, a keyboard has generated an interrupt, for example, then there will be a particular specific service routine or nothing but a specific piece of code, and by the operating system will run that particular piece of code on behalf of the user, and with that piece of code it service the interrupt. Servicing the interrupt is a thing, but now the keyboard has sent the interrupt, meaning that yeah, you have requested for IO. Now that IO has been available, now that input from the user is available in my buffer and all, so that will be informed through interrupt. And whenever that interrupt arrives, then the system will come to know about, our operating system will come to know about, yeah, this particular interrupt is generated by the keyboard. So therefore, the corresponding keyboard service routine, keyboard interrupt service routine has to be handled. So that keyboard service interrupt routine will be available at some particular location of a memory and all. And that particular location will be maintained by some table, like for example, interrupt table and all. And where that particular interrupt service, keyboard interrupt service routine will be numbered as some 13, for example. And in the table, the 13th location, it provides the address of the starting address of that particular interrupt service routine. So that way, so whatever the device, if it causes the interrupt and all, we'll come to know by using the interrupt table, interrupt vector, you will come to know that about what interrupt, which one has caused the interrupt, and where that particular interrupt service routine is available. And once you come to know about the interrupt service routine, then that particular starting address will be placed in the PC, and then the CPU executes that interrupt service routine. And that interrupt service routine is nothing but its job is to again transfer the data, whatever is collected by the keyboard controller to the specific memory location and all. So that way, each device or each interrupt has a specific service routine will be there, and all these service routines are maintained by the operating system in the form of a table or in the separate memory locations and all. And based on the strategy, the interrupt will be identified, and then the corresponding interrupt service routine will be executed by the CPU. So with that, the corresponding task will be performed and all. And as we already mentioned that the interrupts or these events can occur in a different ways, in a different reasons. One thing is that, as I mentioned, that the other components of the computer can generate interrupt, right? And there are other reasons like sometimes when the user program is in execution, and this user program itself may generate or may when it's execution, some unusual event may occur. Like for example, we have seen like when it performs some arithmetic operation and all, a overflow may occur. It means that the result, whatever required to store it, it crosses beyond the limit, like because it's meant for 32 bits. And suppose if you get a overflow, for example, then it leads to error and all. So that is unusual thing. So at that time, the system, the program, when it's execution of program itself, it generates like the interrupt, or that's not to be exception and all. So exception will be erased, and then again, by knowing this exception, the nature of the exception and all, a corresponding exception handler or is nothing but exception service routine will be carried out. Like so therefore these interrupts and these exceptions and all we use interchangeably. In general, the exceptions are means these are the interrupts that are generated by the software. That means when you are running a code, either it's a user program or like a system program and all, and when it leads to some unusual things like some exception, it rises to some like unusual things these things, like for example, as I mentioned, overflow or a division by zero, or for example when you're trying to decode instruction and you will get a opcode which is not there or not known, which is not valid opcode. So likewise, all these things are these are generated because of the execution of the program and all. So those are known to be exceptions and all. These are known to be exceptions or a trap. Exceptions as a trap. And for every exception and all, there will be a specific routine, a specific service routine will be there, and that will be executed. So with that, sometimes no, you can that exception routine is nothing but simply it generates the display the error and all, mentioning about, yeah, this is the type of some 500 error or something like that, whatever. So like different error codes will be generated. So with that, the user will come to know about like what is the why the program has been stopped or why the program has been interrupted, and also that way he will come to know, and then he will try to modify the code, and again he will rerun. Or sometimes no, like some programs or some high level languages, they will ignore the exceptions and all. Even though the exception occur, the program will continue. That depending upon the like the nature of the languages and all. And basically the way the operating system will function will be it's interrupt driven. What it means here is that usually the CPU runs the user programs, like the user will interact, the user will interact the computing system. It's nothing but the user program is running, whatever. Suppose if you press some command, it means that it's a user program, it's running and all. So whenever the user program is running, or if it requires any operating system to perform on behalf of that, so all these things will be carried out. What I mean to say is that the operating system will be executed by the CPU only. It will be done by using by with the help of interrupts. It will be driven by the interrupts. Either it may be software interrupts or it may be hardware interrupts. So software interrupt means suppose the user program is executing. As I mentioned, suppose the user program needs some IO, some keyboard inputs, some input from user and all. So at that time, the user program, one of the commands will be like a scanf function. At that time, that library function will in turn to execute that particular function call. It needs the IO record because it needs the input from the IO. It needs input from a keyboard. So you cannot the user program or user instruction cannot directly interact with that particular IO device and all. So therefore, it takes the help of the operating system. That means it will internally call the operating system routine, and that operating system will understand that what is the requirement, and then it interacts with the corresponding device controller. It will perform its job and all. So that way, the user programs will make use of the operating system services by using library functions or by using APIs and all. So they make use of the operating system function services and all. And so that way, and not only that, even the peripherals also to carry out their services and all, it also make use of the operating system services by using the interrupt center. Because as I mentioned, suppose when you request for IO and the operating system will assign some task to the IO. That means, yeah, it says that yeah, IO is requested by the user and all. And whenever the user provides the data, at that time it will be collected, it kept in a local buffer, and afterwards that particular device controller will inform the CPU, because then the CPU is running some other program. Now it interrupts the CPU, says that the device is ready, or your keyboard request is ready, the IO is ready and all. Then the CPU will again will make use of the operating system, and it performs that particular task. So that way, the operating system will be executed by the CPU based on the interrupt driven. That means, so whenever you require the operating system, at that time, the CPU switches from the user program to the operating system by calling an interrupt. Whether that interrupt may be either the hardware generated interrupt, or it may be software generated interrupt or exception, whatever. So that way, mostly the operating system will come into the picture because of the interrupts, either software or hardware interrupts. Yeah, these things we already discussed about that. Suppose when an interrupt is generated, how do we know that what is the type of which interrupt it is and all? So that we can able to identify that by using different various techniques are there, and one of them is a polling technique, and other one is the vectored interrupt technique and all. Yeah, right. And this is a diagram where with which you can able to understand the simple thing, whatever I have mentioned. For example, when the CPU is executing the user program, and here you can see these vertical lines indicating that the CPU is executing user program, and the user program at this instance, it is requesting for IO. It is requesting for IO. Right, you can see the top here. There are two plots are there. So the first one, the top one, is that it's like the CPU like actions, and the bottom one is the IO device actions and all. And here the user, show me that user program is executing here, and here at this instance the IO is requested. That means user program is requesting IO. Then it informs to the it contacts the it's nothing but IO cannot be done directly by the user program. So therefore it internally passes the control or passes that information to the operating system. So operating system, because IO means actually it has to deal with the one of the IO devices. So therefore the operating system will will come to know that actually which IO device need to be contacted. Then by using that specific device driver, like suppose it need to derive receive the data from a file. So the file will be there in the disk. Suppose if you receive the data, want to receive the data from the keyboard, then it has to contact the keyboard controller. So likewise, or otherwise, suppose for example, your function is like a printf function. It means that you need to print some message on the display. So then you need to contact the graphics adapter card, something like that. So that way, the particular device driver will contact the specific controller. And then you see that upon IO request, it contacts the specific device controller. So till that point, actually, you can say that it's idle. That means IO device is idle. Then after initiating that IO, that means that is informed to the device controller, then the device controller will perform the job. That means will capture the input from the particular device, whether it may be from a disk or whether it may be from the keyboard. It performs it will collect the data, the desired data requested by the operating system and all. And the moment once it receives the data, then the device controller will come to know that whatever the requested data that is completed, that means that has been captured, that has been arrived and that's ready. So now that information will be informed to the again the CPU by generating the again interrupt and all, by generating the interrupt. So after you generate this interrupt, actually here this is the interrupt that is generated by the user program requesting for IO. and afterwards this CPU runs some other program, right? Some other program it runs. So the CPU executing some other program, and now this IO device, the IO device controller, it is receiving the data. That means both are happening parallelly. And afterwards, whenever the data that is received by the particular device controller, when it is done, when it is completed, then again that will inform to the CPU. It will inform to the processor. So how it will do? Again, it will generate an interrupt. Here in this case, it generates a signal. It generates a signal. Earlier here, it is generated by software, because when the user program, if the function, if the that is if the one of the if the instruction is like a scanf function, or instruction like a printf function, at that time the corresponding like library function call, it generates it tries to contact the CP, it tries to contact the OS. So that way the OS will come to know, and some of the parameters may be passed to the OS, and also that way the OS will take that will run for some time, and then afterwards the OS will pass those parameters to the device controller, and the device controller will carry out its job, and the CPU runs some other program. And now when the device controller has completed its job, right, then the device controller will inform to the CPU by generating an interrupt. It's nothing but just by generating a signal to the CPU, one of the CPU pins. Then the CPU will realize that the interrupt has been occurred from one of the devices and all. Then by using either interrupt vector table or by using polling mechanism, it comes to know that actually which has been caused the interrupt, and then that interrupt service routine will be executed over here and all. You can see here, this is the normal user program execution, and here coming to the lower portion, this one, right? So this indicates that the IO interrupt handling is nothing but when the device contacts, when the device sends a signal, it means it generates interrupt, corresponds to this interrupt. So the CPU generates here, the OS code will be run here, the corresponding interrupt service routine will be run over here. And with that, whatever the data that is collected by the device controller, so it will be passed on to the memory or whatever. So that will be done by using this interrupt service routine. And once this interrupt service routine is over, again, the CPU will execute the normal user programs and all. And here at this point, again, the user program may request IO, right? And then afterwards, here again, the device controller will tries to manage to collect the data. And here the device controller completes the data, completes the receiving the data, or completes capture the data. Then afterwards, again, it will inform to the CPU by generating the interrupt and all. And then with respect to this particular interrupt, again, the operating system will run the operating system code, that is nothing but the particular interrupt service routine will be executed during this portion, right? And once again this is completed, then again the user program. So likewise, the CPU will execute either user program or the operating system code, or kernel, right? So user program is normal user application programs, whatever we are running. And at that time, whenever the operating system, whenever it requires any IO or whatever, and also at that time it runs the OS code. So that way here, these are the portions, the lower here in these pulses and all, the bottom are the lower level corresponds to the OS execution or OS code execution, and the high level corresponds to the user execution. This is just for interpretation purpose. Whereas here in case of IO devices, you can see the bottom figure where it indicates the high corresponds to that IO devices are idle. That means there is nothing to do. And then whenever and here the lower level corresponds to that IO is functioning. That means the particular device controller is active, and it tries to receive the data or tries to like upload the data, whatever is happening. So this way, by using interrupting mechanism, interrupts and all, so the CPU will handle the OS will come into the OS will execute, and the OS will perform its services and all. Right? Okay. Yeah, and again the same thing. While performing the OS, operating IO, sometimes no the corresponding user program and the CPU will be blocked. Like it means that suppose when a user program is executing, you are getting you encounter the scanf function. It means that the user, it expects the input from the user and all. So at that time, maybe there are instances where sometimes where that depending upon the the implementation and other things, where the earlier thing where the particular program will wait for the keyboard until the keyboard until the input arrives. Till that, the user program or the CPU also will be waiting for the input and all. And once the input arrives, then the CPU will carry out its execution. So it's known to be like, this is one way. And other one is that actually here, when IO is initiated, when IO is requested by a user program, and the control returns to the user program immediately. It means that actually, again, IO is just initiated, just whatever the previous diagram, whatever we have seen. IO is requested and it will be initiated by the operating system, and the CPU will run some other program, user program, without waiting for that. So that way here, these IO requests can be viewed as a blocking, sometimes known to be blocking calls and sometimes known to be unblocking and all. Blocking calls means it whenever request for IO, it keep on waiting for IO completion, and then only it returns back and then it starts execution. And unblocking means actually it requests for IO and then afterwards it runs the some other portion of a user program to carry out further and all. Then this particular slide is to give just a basic terminology related to the various the units that are used for representing the storage and all. As we're already aware of that, there's nothing, no explanation is required, like a byte, words, kilobytes, megabytes and all, because the later slides and all we are discussing about the storage. So therefore, this is the preliminary slide which used to give very the basic definitions of the information storage, right? And so this storage structure we already discussed in the just a few lectures before. So therefore, we are not going to discuss here. As we have memory hierarchy, already we had discussed from cache to the secondary storage, and their nature and all these things. We have discussed the storage structure. And yeah, we have discussed all these things, caching and all these things. And here in this context, the device driver means actually here the operating system will maintain the varieties of device drivers to handle the various peripherals that are attached to the system and all. So that way, the device drivers of this operating system will provide the uniform view to the kernel and all. Kernel means it's basically the programs or the codes that are above the device drivers. Device drivers are the codes or the piece of codes or the specific routines. Those are the ones where you can say that they are very close to the hardware because they directly speak to they directly interact with the various peripherals and all. So therefore, if you view that the kernel operating system as like a set of routines, and if you view that as a different levels, at a very bottommost level, the operating system or a kernel contains the device drivers and all, because they are the actual software, the piece of codes where they used to interact with the devices directly and all, right? And the above routines, they provide above kernel routines for them. The device drivers will provide a uniform interface, like whether the device may be either a disk or a keyboard or like a graphics or a output device, whatever. It will not bother. It will not give a uniform view to the remaining kernel routines and all. So that way, these device drivers there are like varieties of device drivers. All of them together will provide a uniform interface to the rest of the kernel and all. Whatever may be the device and all, whether it may be like a network adapter or whether it may be connected to some USB drive or some other thing, whatever. For all of them, or it may be CD, whatever. All of them, it provides a uniform interface. Doesn't bother about that. Right. So this is the hierarchy. We already come across these things, and you can see that the top three corresponds to where the CPU can able to access up to this point, like main memory. And the solid state disk and hard disk and all, they will come under the secondary storage. That means hard disk, and the solid state disk means like a flash memory. Both are non-volatile here and all. And the first three are like a volatile one. It means that whatever the data that is present in these storage media, so there it is there as long as the power is there. Once you switch off the power, and the contents will be lost. Whereas here from below this one, all are the non-volatile one. And here the solid state disk and hard disk are usually come under the secondary storage. They try to back up the main memory. It's like for them, the main memory will act as a cache kind of a thing that we have seen, right? and the bottom two are the devices which are the storage devices. So they can be, they need not be present in the computing system all the time and all. So whenever you require, you can place that particular, you can add that storage to the system, like optical disk, either in the form of like CD, DVD, or whatever, and the magnetic tapes, which is much larger storage media. So it means that the bottom two will be known to be ternary storage. It means that whenever you require, because their usage will be very infrequently used and all. So therefore, whenever you require, and at that time you can attach these storage media, and it can fulfill the carry out the specific tasks and all. So that way, this is the overall storage hierarchy. This we already come across. And caching, I'm not going to discuss because all very recently we covered all these topics and all. Then coming to direct memory access means here the concept of direct memory access means, suppose if you see that suppose if you want to transfer data between the disk and a main memory, and so by using the interrupts, the way the data transmission takes place will be, because the memory, the bus size will be like either 32 bits or 64 bits based on the width of a bus and all. And here, the normal way, the data transmission or like the information communication between the disk and a main memory, or a high-speed device and a main memory, will be like, it will go by word, or whatever the size of the bus will be there. No, so that means, like for example, if it's 64 bits, that means at a time in a one cycle you can able to transfer 64 bits, right? And the way it will be carried out will be like, for every 64 bits you need to generate an interrupt. That means you are transferring 64 bits and it should be acknowledged. Then, and again, a new 64 bits will be transferred. So that way, the data transmission takes place between the memory and the other peripherals will happen like that. But it's a very like a hectic process. Suppose you want to send a large blocks of data, large volumes of data between the disk and the memory. Suppose you are reading something from a disk and placing into the main memory, or you are placing the some pages of data from main memory to the disk and all. So at that time, going by this way, by using with the help of interrupts, transferring the data from peripheral to the main memory or main memory to peripheral and all, it takes huge amount of time. So to avoid that, there is another way of transferring the data when you interact with the high-speed devices and all. It's known to be direct memory access and all. So here the idea of direct memory access means, here in case of direct memory access, here the CPU don't intervene in between the data transmission. That means the CPU will be informed at the beginning that actually now the data will be transferred by using between these two device, memory and high-speed device, and the block sizes are of this much size of like for example, like a block size equals to 1 MB or something like that. So it means that the CPU, it will take first inform to the CPU, then afterwards the bus will be given control to between these two memory and the particular device. And then for every block transfer, it will be informed to the CPU, like saying that yeah, now the first block has been transferred. The block size equals to maybe order of like hundreds of kilobytes or megabytes like that. So during the block transfer, the conventional way, like the transfer is not with respect to the interrupt and all. The interrupt will be generated for every block transfer. It means that after transmitting 1 MB of data, then again it will check with the CPU whether the CPU requires the bus or not. If the CPU doesn't require the bus and all, then it will take inform to the CPU that it is going for next block of transfer and all. So that way, in case of direct memory access and also the data transmission takes place between the high-speed devices and memory directly without the intervention of the CPU. Otherwise, every time the CPU will be involved in the transmission, normal transmission. See that, for example, we have seen that in the keyboard controller where once the user has given the input, then the keyboard controller will inform to the CPU. Then the CPU will inform to will use the OS routine to perform the transmission. Then afterwards, again the keyboard controller. So likewise here the CPU will be involved for carrying out the data transmission, like almost like a byte by byte or word by word or like a smaller blocks and all. But it will not. It will be like consumes lot of time when you are really attempting to go for the large data transfers, like from disk to the memory and some other high performance device, high speed devices. So at that time, this there is a controller known to be direct memory access controller, DMA controller, and that takes the control over the CPU, and then that makes use of the bus and takes care of the two devices which need to the data transmission has to be carried out, and with that the data transmission will be carried out. It means that it maintains the clock, it maintains the counter, everything, and then it just check that actually whether the entire block has been transferred or not. After the entire block has been transferred, then it checks with the CPU, because maybe CPU may request, may need the bus, may need the bus. So if it needs the bus, then the CPU will be given the bus, and afterwards again the DMA controller will take over the bus and it carry out the data transmission. So this is another scheme of data transmission where high speeds data transmission at high speeds can be carried out. Yeah, this is the the overall scenario where you have a CPU and you have a memory, we have a devices will be there. This may be disks, disk controller or whatever. The CPU will inform so when the user program is executing, if CPU, if that program requires some IO, it send the request to the IO. It's not directly to the, it will not directly contact with the help of IO routine or IO. It informs to the device, and then the device may interact with the CPU directly also. Sorry, not directly. Again, the device again will exchange the data from CPU to the device. Again, it's not directly because it's with the help of the IO, with the help of, sorry, OS, operating system routine. Because you see that when the CPU requests IO, it may need some parameters to be passed. And then again, once the data is available at a device controller, again the data has to be sent to the CPU. So it will be done through the by using OS, right? So therefore the data can be transferred in either side from CPU to device and device to the CPU. And interrupt, it is only from the device to the CPU, because when the device is ready or when the device has done some work and it is ready to be delivered the data, at that time it generates interrupt and all, right? And again here between the CPU and the main memory, again the CPU contains the cache, so in between the interaction will be like instruction to fetch the instructions and all, because it uses the cache and all. If that's not there in the cache, it make use of the as a backup, it contains the main memory, and from main memory it fetches and doing that. And similarly for data movement. And this is a DMA. So DMA means actually from a device to a main memory, the data transmission or information communication between these will be done directly without the intervention of the CPU and all, without the intervention of CPU. Then at that time, you can able to transfer data rates at very high speed at a memory access times or the memory speeds and all, right? Otherwise, no, for every data transfer, for every by every word or every two words of transfer, the CPU has to be informed. Let me CPU has to initiate for everything. So that is waste of time for both CPU as well as for actual data transmission also. So here in place of that, now the DMA controller will be there, and the DMA controller will take responsibility of that one for transmission of the data between the device and the memory. Yeah. Then yeah, so far we discussed about very basic computer components and its interaction with the help of OS and all. And now when you look at the various computer system architectures, yeah, these things just to, like as I mentioned, no, this is an overview. Like we have systems, like so far we discussed about the systems having a single processor, and the application will be like a general purpose processor, no, whatever. It's like, you know, our PCs, normal desktop PCs, where it's a general purpose processor. So we'll try to execute the varieties of applications, varieties of tasks on that, right? And now as the technology improved and most of the systems are now equipped with the multiprocessors and all. It's not one processor. In place of that, we have multiprocessors. And so these multiprocessors are also known to be parallel systems or like tightly coupled systems and all. Because here, the reason for tightly coupled means here, all these processes are there within a system, or in one system it will be there. And if you give a task and all, that task will be distributed among these processes, and with that, the task can be performed in a less amount of time in a very efficient way. So and all these processes are also connected, well connected. So therefore, it's known to be a system having multiple process within a single system. It can be viewed as like tightly coupled systems and all. And whereas if you have like there are loosely coupled systems are known to be clustered systems and all, where we have like individual systems are there, and those individual systems are connected by using appropriate network or whatever. And there also we can perform a similar task. Suppose have any complex problem is there, and that complex problem can be properly divided and can be assigned to those multiple systems, where each system contains again one or more process will be there. So those are known to be loosely coupled systems. Whereas here, a system having a multiple process inside, they are known to be tightly coupled systems and all. So that is the distinction between the tightly coupled and loosely coupled systems. And the advantages of these multi-process systems are like obvious advantages, like increases the throughput, like since there are multiple number of processors more, so you can make use of all the processors simultaneously. So with that, the throughput can be increased. And economy of scale. Economy of scale means suppose you have a system having 4 processors inside, and with that the throughput will be increased and other advantages are there. But at the same time, it is very economical also. It means that instead of 4 processors in one system, and suppose we want to have like 4 systems having each having only one processor inside, so the cost of that 4 systems together will be much higher, much higher compared to a system having 4 processors inside and all. So that what I mean to say is that these multi-process systems are very economical, and compared their throughput is much higher throughput compared to single system and all, and the reliability also will be more. So it means since you have multiple process, and if there is any problem with one of the process, the immediately the other process will take over that with a graceful degradation. Otherwise, suppose the system having only one processor, and if there is any problem in that processor, in malfunctioning or something, then the entire system will be collapsed. Whereas in case of multi-process and all, so since we have a multiple process, if one of the processor is somewhat behaving strange or something, if it is giving erroneous results or something, then we can make use of the remaining process to perform the task and all. So that way, reliability can be increased. So these are some of the advantages we can view towards multi-process systems and all. Then for managing these multi-process systems, we have 2 ways. One is the asymmetric multiprocessing and symmetric multiprocessing. In the context of asymmetric multiprocessing means here we have set of processors are there, and in that one processor will play a role of like a kind of master. It means that that particular processor will try to coordinate the other process and all. Like for example, whatever the tasks that are given, we have multiple programs are there in your memory and all, and the way these programs are allocated to the various CPUs, various other processors and all, that will be taken care by one processor, one designated processor and all, and the remaining processors will just perform the job whatever they given to them. So that kind of a scenario known to be asymmetric multiprocessing. It's a kind of like a master slave kind of a thing. There will be one designated processor which performs the task of scheduling or coordinating the jobs and all, and the remaining process just whatever the scheduled task they will carry out. And in case of symmetric multiprocessing, there is no such a distinction and all. Like all processes will be treated equally, and as such that there is no processor will maintain a role of master or whatever. And here the operating system will take that responsibility and it tries to coordinate and tries to provide the like make the all systems to all process to be engaged all the time and all. And again, if there is any some problem, again the other process will take care of the jobs that are assigned to that particular processor and all. So that way there is symmetric and asymmetric ways of handling the multi-process systems and all. And anyway, this is the scenario where you have multiple processes on different chips. And there are ones where you have a multiple process on the same chip, right? Multi-process on same chip. This is known to be like a dual core system. And now we have a quad core, octa core systems also. Here on a single chip, the multiple CPUs will be placed. multiple CPUs will be placed. Whereas the earlier one here, each CPU will be placed in a separate chip and these chips are interconnected. Whereas here, all the chips, all the processors are placed in the same chip. So with that, actually, the speed of communication between across the chips and all, it will be higher compared to these ones. And each processor will be in a separate chip and all, right? So those are the advantages between the dual core or multi-core to the like multi-chip systems and all. And yeah, clustered systems, as I mentioned, they are loosely coupled systems, right? Clustered systems means here they are also similar to multi-process systems, but here the multiple systems are put together or working together. So basically here we use kind of network systems where suppose we have a database or have a file system there and all. So instead of replicating the file system or database for all the systems which are performing a specific complicated job or whatever and all, instead actually the storage or a file system will be placed in one of the system and other systems and all connected to that, and with that you can make use of that particular storage or a particular file system to perform its activities and all. And again, here also we have used multiple systems are involved. So the way of the functioning of those multiple systems together will be either asymmetric clustering or symmetric clustering and all. Asymmetric clustering or symmetric clustering. The way that asymmetric clustering means one machine will be used in the standby mode and all, used to monitor that. And whereas in symmetric clustering and all, it's not the way and all. Each system will also look at monitor the other systems. So that way, if there is any failures or if there is any problems and all, so the other monitoring systems will handle that. Right, and basically in case of these clustered systems and all, and these things to get a high performance, so the user programs also, if they are written in a modularized wise or like in a parallel fashion, then you can able to see the much efficiency into that when you are running that code, right? Because if the user program is designed or user program is written such a way that there are some parallel components, so that all these parallel components can be run simultaneously on the multiple systems and you can make use of the advantage of that. Distributed lock manager means here when you're handling with these multi-process systems, particularly clustered systems and all, where the systems are separated and they may are acting on the same data or the same files and all. At that time, you should be critical that there are some data which is handled by multiple systems and all. So you should be careful in when you're writing the data or when you're reading the data and all. When you're reading the data, you have to make sure that whatever the data you're reading, it should be the most updated one or the most recent one. So such things will be managed by using distributed lock manager, to be process synchronization and all. So these things anyway we'll discuss later in the next the following chapters and all. So that way, if you have clustered systems and all, you will get advantage, but at the same time, you should see that whatever the data or whatever the files you are managing, they should be they should maintain the data consistency across the systems that they are running and all. So now I think, yeah, these are the clusters. Anyway, these are the diagrams just to illustrate that. Okay, we'll stop here at this point and we'll continue this in the next class. It's on 28th February, Monday. Okay, and I'll stop here. Let me. Yeah, this is introduction. I thought of actually come the whole chapter today itself because these things, most of them were or you are aware of that. There is nothing to explaining specifically and all. That's why I'm just going, I thought of covering that with going a bit faster and all, because the actual chapters, the more detailed ones, whatever you are covering, these things in a detailed way, they will be discussed in the later chapters and all. When you go for a process management or various other aspects, thread management and all, where you can see the more details and all. So there you can able to spend more time. So these are the ones where just gives you an overview of the functionality of OS, what are its components and all, so that are covered here, and more details you can see in the individual chapters and all. So let me stop the recording here.